In the next set of lectures, we're going to talk about building and interpreting Lewis dot structures and chemical structures in general that are represented in two dimensions. So we now have a little bit of idea of what covalent bonding is and have some of the language around it, like lone pairs, bond, and then also an idea of how to determine the number of covalent bonds an element is likely to form within a molecule. So we'll then take those skills and put them into practice here. First, I want to show some examples and define a few things about these two-dimensional structures we're going to look at. So chemists in general like to communicate information by abbreviating as much as they can and drawing as much as they can. And so they communicate information about covalent bonds by using these 2D pictures that represent how the atoms are connected together. It's like, this carbon's connected to this oxygen is important information that you don't get from just the chemical formula, which is like giving you the number of atoms you have relative to one another in the actual molecule, but it doesn't really describe the order they're connected at all. And that order is important because that actually creates the geometry, the shape of the molecule that defines its behavior. So Lewis dot structures have a lot of information visible still. It shows all hydrogens and carbons, but it shows less information about the geometry with which they're all connected. A further abbreviation that's common is what we call line structures. We use them a lot in organic chemistry, and we use them a lot in biochemistry and anything where we're talking about larger molecules. A line structure is going to delete even more information or abbreviate, where it won't actually show the carbons written out as C's, and instead they're just the corners of lines. And we remove all the hydrogens because there's always so many hydrogens. So here's some examples of both. So I have a Lewis structure, which we're going to walk through the steps of how to build these in a bit. But you can see it's represented with element symbols for each of the atoms. And so each of the atoms is represented. So like this is a carbon atom. And our H's are the chemical symbols for hydrogen. So that's saying here is a hydrogen atom. And these are connected together. These lines here represent the bond. And so those lines in between the carbon and the hydrogen atom represent 2 electrons that are shared between those 2 atoms. And it's also telling us that the hydrogen atom is connected to the, or sharing with the carbon atom. And so butane has 4 of these carbon atoms all lined up, sharing electrons with each other. And they're not sharing the same electrons, right? So each carbon is sharing 1 electron with a hydrogen, 1 electron with another carbon, 1 with another carbon or hydrogen, and then 1 of their electrons with another hydrogen. So remember, it had 4 electrons in its outer electrons, and each one of them is separately being shared with a different atom. And that is creating 4 bonds. And that each bond is going to represent 2 electrons because the other atom is bringing in an electron to share 2. And so that carbon starts to experience having 8 electrons attracted to its nucleus, just like neon, its closest noble gas. Take me a minute to think about it. Now, in our line structure, we remove some of that information and we just assume our reader can kind of fill in the gaps. And so what we do is we first remove the hydrogens because they take up a lot of space, right? And so we're going to assume if nothing is drawn, that there is a hydrogen there, if there is a need for a bond for that element to have those 8 outer electrons. And then the carbons we represent at the corners. So each of the corners or ends of the line are a carbon. And so this carbon right here, that's a corner, is this second carbon right here in our Lewis dot structure. And you can see there's no hydrogens on here at all. We assume that any carbon that is bonded to only one thing will then have 3 hydrogens. And any carbon bonded to 2 other carbons will have 2 hydrogens. And so these line structures can really simplify big structures, but they also make it hard to kind of think about the details of the bonding of each of the atoms. But it's really nice to do for big ones. So here is THC as a line structure. And there's a little bit more detail, like we typically will see these line structures, but then still see hydrogens if they're in like a geometrically interesting position, or if they're bonded to an oxygen, like you see here. Like this is really going to be an oxygen bonded to a hydrogen like this. They kind of abbreviated away the line that connects the oxygen and the hydrogen that represents the 2 electrons that they're sharing. And so you'll see a lot of variance in how much these line structures are abbreviated if you're looking at any resources in textbooks or online, especially about larger biomolecules. So let's point out a few other things here besides just that OH. We also see these wedges and dashes. These are trying to represent, sorry. It's just giving us information about the 3D structure of this molecule. And not all of this line structure is communicating it in 3D. It's not perfectly written in 3 dimensions, but it's highlighting an important part that has, so really this would look like a carbon. It would have 2 bonds, and it would have going up and down, or sorry, 3 bonds to other carbon atoms. Those would be here and here and here. And then 1 bond to a hydrogen. And this hydrogen could be either kind of coming out at the viewer or going back away from the viewer. And the wedge indicates that it's coming out. So a wedge in chemistry that is filled in means it is coming out of the plane of the paper. I know dashed line, like a dashed wedge, I guess, that indicates that it's going behind the plane of the paper. So that's information about the 3-dimensional structure. We'll look at that a little bit later, but it's kind of haphazard. So you'll kind of see these elements that people think are important brought in. One last one to point out in this structure right away is these double lines right here. All of these double lines represent double bonds or two bonds. So a double bond like this equals 4 bonding or 4 shared electrons. Let's say that. So each line represents 2 electrons. So if there's 2 lines, there's 4 electrons. And if there's 3 lines, there's 6 electrons. So here is that same structure, but drawn out using Lewis theory. So this is the Lewis dot structure. Of THC. THF. It's a different molecule. And you see, it definitely is visually more stimulating, right? Like there's just a lot more written out. It's the same information as the other one. And I've highlighted our double bonds, and we also have our oxygens. I put in a different color to make them stand out. But it's a lot of hydrogens. And sometimes that just amount of like the number of hydrogens in any of these molecules can be visually overstimulating and make it actually hard to see the shape of the molecule and look for pieces of information like the double bonds or triple bonds or oxygen atoms or things like that, or lone pairs. Actually, I forgot the lone pairs on this one. I forgot to put 2 lone pairs on each of these oxygen atoms. So we are going to now kind of talk through how to build these Lewis structures that have all the information, because those are going to be the easiest for us to work with to make predictions about the behavior of the molecule. And we're going to kind of need all of that information. The line structures aren't something that I really expect anybody to be proficient at doing. It's just that you're going to be exposed to them so much. I think it's important to talk through how to interpret them when you see them. I'll try to provide Lewis structures in this class and not assume that everyone's ready to look at the different like add on the layers of information that have been removed in one of the line structures.